So we were doing isomerism today. In the isomerism we have seen that first one, that is structural isomerism. Now we have the second type of isomerism, which is called as stereoisomerism. So isomerism in coordination compounds is of two types, structural and stereo. Stereoisomerism we are going to discuss now. What is stereoisomerism? Complexes having same chemical formula and molecular formula, even chemical bonds, I mean structure also almost same, but have different spatial arrangement of ligands are called as stereoisomers, meaning three-dimensional arrangement of atoms is different. We will understand more when we go for the examples here. So stereoisomerism is of two types. One is called as geometrical isomerism, other one is called as optical isomerism. So we'll focus now first on geometrical isomerism. Yes, geometrical isomerism. Before I give you the definition, I want to tell you the meaning of 3D space or geometrical. See this? If my coordinate number is 4, I told you shape possibly is two types. One is tetrahedral or square planar. If my coordinate number is 6, possible shape is octahedral. We know that, you can see here. Right, now, so tetrahedral, how we draw? Two-dimensional way. We have the metal here, 1, 2, 3, 4. Right, this is your tetrahedral. What about square planar? I have metal 1, 2, 3, 4. Oh, sorry. Yeah. Yeah, it would be nice if I use like this, square planar. So square planar like this. Okay, so both of them when the coordinate number is 4, meaning if at all I have 4 ligands, my shape is one of the two. Now what I want is the bond angle between any two bonds in tetrahedral is 109.5 degrees. 109.5 degrees. Any two. You take let's say A, B, C, D. I'm taking either AB you take or BC you take or CD you take. Any two bonds, the bond angle is 109.5 degrees. Whereas if at all you see the square planar, let's say A, B, C, D. What is the angle between AB? AB will be 90. What about AC? AC will be 180. So there are two different bond angles we have in square planar, meaning three-dimensionally there are two different arrangements in square planar, but tetrahedral we have only one type of arrangement. Therefore, geometrical isomerism is not possible in tetrahedral complex because all the bond angles are equivalent in all ways. Once again I repeat, in tetrahedral complexes all the bond angles are same, therefore all the positions are equivalent, therefore we cannot have isomers. But in square planar, if at all we have 90 possible, we have 180 degrees also possible, therefore we have two isomers. For example, if at all I have sorry, I use different color pen. Yeah, I have 4 complexes, A, B, C, D. If I am talking about position A and B, the angle is 90 degrees. If I am talking about A and C, the angle is 180 degrees. Now 90 degrees angle we call them as cis form. What do you call that? Cis form. If at all I am talking about 180 degrees, we call them as transform, meaning they are next to each other means cis form, opposite diagonally means transform. So we have cis location and we have translocation in case of square planar complexes. Next, if you see octahedral complex, I think I can do square planar first, then I can go for octahedral so that we don't have any confusion. Now we'll go for the next previous slide. So what is geometrical isomerism? Complexes having same molecular formula and same ligands but differ in their three-dimensional arrangement of ligands is called as geometrical isomers, and the phenomenon is called as geometrical isomerism. And geometrical isomerism is very commonly found in complexes having coordination number 4 and coordination number 6. So what do we do first? We'll see geometrical isomerism in compounds containing square planar geometry. Yes, square planar complexes having Ma2B2. Be careful, you will see this kind of formulas very often in textbook. Don't get confused. M stands for metal, A stands for first type of ligand, B stands for second type of ligand. For example, if at all I want to make, let's say my metal is platinum. A2 means what? I have one ligand, two types. I have one ligand twice. For example, if you see, I have two ammonia. So instead of A, I can write ammonia. Two are there. And B2 means what? I have different ligand, two molecules. So I have Cl2 here. So wherever you see Ma2, B2 or somewhere, M means metal, A or B, what are the X, Y, L, any terms you see, they are nothing but ligands. Don't worry too much. Okay. So when you have square planar complex, I have metal, I have my square planar geometry. So if at all I have two similar groups with 90 degrees, meaning adjacent. For example, I'll say 1, 2, 3, 4. Now tell me, which are the cis forms here? Which are the cis locations? 1, 2 is cis, 1, 2 is cis, 2, 3 also cis, 3, 4 is also cis, 1, 4 also cis. So I have 4 types of cis. 1, 2 I can write, 2, 3 I can use, 3, 4 or 1, 4. What about trans? Trans means I have only two ways, either 1, 3 or I have 2, 4. So these are the trans locations. So cis form means what? Isomer in which two similar groups are on the adjacent to each other positions. Transform means what? Isomer in which the similar groups are on the opposite side, meaning 180 degrees. Let's go for the examples now. So if at all somebody asks you, write the cis form and transform for the above square planar complex. What do you do? Yes, I'll write cis form first. What is the shape we have? Square planar. Let's say this is my square planar complex. I have my platinum in the center. I have my platinum in the center. Okay. So what I have now here? I should write 2 ammonia. So I can see when I write cis form and transform, I will be always doing with respect to two similar groups. So I can use either 2 ammonia as my reference, or I can use 2 chlorine as reference. I am using chlorine as a reference. So I am writing a cis form with respect to 2Cl. So if I write my Cl number 1 here, where should I write one more Cl for cis form? Should I write here? Should I write here? Should I write here? If you see clearly, definitely my answer should be either this one or this one, but not this one. Why? Because next one. So my new Cl should come either here or here. So I'm writing this one. So this is 2Cl. If your 2Cl are used, what I have remaining? I have ammonia. So ammonia 1 comes here, ammonia 2 comes here. So this is called a cis form. What do you call this? Cis form. Now can you help me please to write with transform? Pause the video and write on your own and verify your answer. I am writing transform on my own. Please take a book and try on your own to write transform of the above isomer with respect to chlorine. Yes. So this should be your answer. My transform is like this. Okay. So if at all your answer is right, you've done good job. Keep it up. If at all you have any doubt, please get back to me. Yes. So this is your cis-trans isomerism or geometrical isomerism in square planar complexes. In where I'm talking about? I'm talking about in square planar complexes. Now going to the textbook example what they gave you. So you can see here this is cis form and this is trans form. So this is cis and this is trans. You remember I told you in the beginning of the video, cisplatin we call this one as. Cisplatin we call this as. Common name, cisplatin used in cancer treatment. This is called as transplatin. So now you understand why I call as cis, why I call as trans, because two similar groups on the same side, two similar groups on the opposite side for the transform. Yes. Now going to the next one, geometrical isomerism in octahedral complexes. Many students will have confusion with respect to what is cis form, what is transform in octahedral complexes. It's very important for you to understand. So be careful, pay attention here when I'm doing. Look at this ones. So what is this here? Any two positions which are separated by 90 degrees, we call them as cis forms. And similarly, any two positions which are separated by 180 degrees, we call them as transpositions. Now, for the sake of clarity, I want to give the numbers for the octahedral complex. Here, what you see in the image. 1, 2, 3, 4, 5, 6. While when I am drawing, I will be having like this octahedral complexes. So 1, 2, 3, 4, 5, 6. My metal will be somewhere in the center. Okay. So numbers how I gave you. If you see the numbers how I gave you, I gave 1 here, I gave 2 here, I gave 3, I gave 4, I gave, sorry, I gave 6 here, I gave 5 here. Am I right? Now, so what are the cis locations? If at all I have asked you to write cis positions, what are the position choose? What about 1, 2? 1, 2 is what? They are cis, right? So 1, 2 are cis forms. What about 2, 3? So 2, 3 also cis. What about 3, 4? 3, 4 also cis. What about 1, 4? 1, 4 also cis. What about 2, 5? 2, 5. Are they separated by 90 degrees? Yes, right? So 2, 5 also cis. What about 1, 5? 1, 5 also 90 degrees, so 1, 5 also cis. What about 4, 5? 4, 5 also 90 degrees. See clearly. You can understand only by this image. You can't understand in this image. So be careful. So 4, 5 also cis. What about 3, 5? 3, 5 also cis. So if you see clearly once again, I get 1, 6. 1, 6 also cis. 3, 6. 2, 6. 4, 6. So we have got so many cis form. So if at all anybody asks you to draw a cis form, you can use any two numbers what you're learning now. No need to stick on to any two what is used by textbook. You can choose any two numbers what I called just now. Okay. So there are so many ways of writing a cis form. Now, quickly tell me transforms now. Transform means what? They should be separated by 180 degrees. If you see here in the image 180 degrees, first one is I'll go for so I use different color. Yes, first one is I go for 5, 6. So 5 and 6 are my transforms. What else? I can go for 2, 4. I can go for 2, 4. I can also go for 1, 3. That's all. I don't have many transforms. But since there are so many ways, but transforms are only 3 I have. Okay. So 5, 6, 2, 4, 1, 3. Kindly be careful. If at all I'm using different numbering, that location, the numbers may change, but positions are important. Remember positions. Don't by heart the numbers. Okay. Yes. So I hope you understood now what is cis, what is transpositions with respect to octahedral complex. Now I'll go for geometrical isomerism in octahedral complexes. I told you, if at all we have to have cis form and transform, we should have what? 2 groups similar. We must have what? 2 groups similar. If at all I have one complex like CO, NH3, 6 times some complex I have, will it show geometrical isomerism? My answer will be no. Why, sir? Why it won't be? Because the rule is what? I should have only 2 groups which are similar, but here all the 6 are similar. So any complex of mx6 cannot show geometrical isomerism. Similarly, mx5, meaning only one is different. I want 2 things to are different, so not possible. mxl5, meaning again 5 ligands are same, one is different, not possible. So mx6, mx5l, mxl5 do not show geometrical isomerism. But which will show? So the second point here, make correction please. Complexes with mx2l4. mx2l4 can show cis form and transform. Meaning what? Which are 2 similar groups? I have 2x. I can make my cis form and transform by using 2x. So what are the shape we have? Octahedral. I have octahedral geometry. Am I right? So I want to make cis form by using x. How to make cis? If I write my first x here, why should I write my second one? Help me out. Can I write here to make cis one more x? Answer is no, because it will be transformed. Can I write here? Can I write here? Yes, I can write, because this is 90 degrees cis form. So I can make here, or I can write here, I can write here, anywhere I want I can write, except on the opposite side. So I can make cis form and transform. So I'll show you an example now. Can we draw the A11 example, cis form and transform? I'll make it. So cobalt 1, 2, 3, 4, 5, 6 I have. Out of 6 I should use only Cl for my cis and transform. So where's my Cl goes? My Cl goes here. Sorry, I'll change color. So Cl1, that's my cis form. How to make cis form? I can use either here, anywhere I can use. I'm using this one. So this is my cis form. So remaining will be what? Ammonia. So this is my ammonia 1. So NH3 1, NH3 2, NH3, sorry, NH3, NH3. So this is what I have. So be careful, the ion has charge 1, so I should have a square bracket plus 1. So this is your cis form. Cis with respect to what? Cl. This is my cis form. What is the transform for this? How do you make transform? Same thing, no? I have cobalt, 1 up, 1 down. So transform, I am taking one Cl here, yes. How to make transform by using this one? It's very simple. If this is my transform, how to make transform? By using 180 degrees, that is this one. So this is my transform. Remaining will be what? Ammonia. So I add ammonia for the remaining. 1 ammonia comes here, 1 ammonia comes here, ammonia comes here, sorry, ammonia, I have a square bracket plus 1. So this is called as cis form. This is called as transform. So do you understand the meaning of cis form and transform? Yes. Now you know the meaning of cis-form and transform. Now I have A12 example. Example A12. I want you to write, let's try. I will help you out here. Let's try A12 example, cis-form and transform. First question. What are the coordination number? What are the coordination number? The coordination number is 6. Sir, how it is coordination number 6? I can see only 2 plus 2. Only 4, right? No. If you remember clearly, chlorine is what ligand? Monodentate. So 2 into 2 chlorine, each one is monodentate, total 2. But En is what? Ethane diamine. If you see clearly, that is bidentate ligand, meaning each En will form 2 bonds. There are total 2 En. Therefore, I have total 2 into 2, 4. So 4 bonds from En, 2 bonds from Cl. Total I have 6 ligand. So therefore, be careful. Complex number 12 also has coordination number 6, meaning that geometry will be octahedral only. I'll go back to the previous slide. I don't have space here to draw the structure of A12. So octahedral complex. So I can make cis-form with respect to what? Can I make by using En? No, because each En forms 4 bonds. I can't make. I can use only Cl. So with respect to Cl, I am making cis-form. Yes. So my Cl1. This is my Cl1. How to make one more Cl? This is my Cl. Then cis-form. Now question is, how will you write En? Because every En should satisfy 2 bonds. So I'll take this bond and this bond. Both bonds should be satisfied by only one En. So how do I write? I write like this. I will write En in the center. Now attach this one like this. Again, one more En. I'll write in the center. So attach the bond like this. That's all done. I'm satisfying 2 bonds by using each En. Total done. 6 done. So this is which form? Cis form. Let's make transform now. Let's make transform. How do you make transform? I'm writing a transform. So I'll use Cl here, Cl1 on top, Cl1 2 down. So I will make transform. So what I should do now? So these 2 bonds must be satisfied by one En. I'll write En in the center. I will attach them. So one En, 2 bonds. One more En, 2 bonds. So this is my transform. So like that I can make cis-form and transform. Let's go for the textbook presentation. See this? This is the complex I'm talking about. So this is which form? If you see clearly here, this is my cis-form, right? Because location 1, location 2, 90 degrees, cis-form. This one is 180 degrees. This is transform. So this is trans isomer. This is cis isomer. Here again cis or trans. What angle we have? 80 degrees, right? Next to 90 degrees. So this also cis form, and this is 180, meaning trans. So like this you can make cis form and transform for octahedral complex. Now, so there is one more special type of geometrical isomerism in octahedral complexes with coordination number 6. What do you call that? I want to give the name here itself. We call them as Fac Mer isomerism. What do you call that? Special type Fac Mer isomerism. Let's see how it is. What I want is, I told you in the regular class during chemical bonding why this is called as an octahedral. If you clearly remember, if I see this shape, I have a face like this, one face. If I turn back, I get one more face by using this one. So I can make, if you see there, I'll get 8 faces. I get 8 faces. Down I get 8 faces. So because we get 8 faces, we call them as octahedral. This face 1, sorry, the face 1, this will be phase 2. Behind 1 there is one more phase, that is third phase. In front of 2, this is your third phase, and fourth one you can't see, it's behind. Similarly, this is 5, fifth phase, and behind fifth we have sixth one, and similar with this one we have one more phase. Okay, so there are total 8 phases. We call them as octahedral. Therefore we call them as octahedral. Now what I want is, for this complex I want to write FAC and Mer isomer. Remember, only complexes having M, A3, B3 formula show FAC Mer isomerism. Meaning what? My ligand 1 should be 3 times, my ligand 2 should also be 3 times. Then only I can have. Remember, if at all I have 2 similar groups, I get cis trans. If at all I have 3 similar groups, we get FAC Mer. How do you write FAC Mer? What is the meaning of FAC, sir? FAC meaning is facial isomer, meaning if at all I have octahedral, this is one phase. Like this I can have how many phases? I can have 8 phases. 2, 3 behind, fourth one behind, I can't see. We can't see that, 3, 4. So if at all this is octahedral, assume. So we have a face like this, we have 8 faces like this. Now this is my, it comes like this shape. Yes. So cobalt, octahedral geometry, 1, 2, 3, 4, 5, 6. I am using A, which is 3 times to make face. How to use one face here? How to make one face? Maybe like this, I guess. By using these locations. So I'll use one NH3 here, one NH3, one more NH3, one more NH3. So I can use 3 similar groups to make the face of a octahedron. So this isomer is called as FAC isomer. If at all I am going to make meridian, what a meridian, how it look like? Yes, I have a octahedral, so this is my meridian. If I make this one L shape, this meridian, so I have one ammonia here, one more ammonia, this is called as meridian. So depending on how the 3 similar groups are arranged, we call them as FAC Mer and meridional isomer. I'll show you the image, it will be more clear. See this. So we can make FAC Mer this one. Why? Because we have 3 similar groups on the same face. See this. 1, 2, 3. They are making a similar face. Okay. Kindly understand here. It's a bit difficult to understand because a 3D image. We can't let's say show clearly on the PowerPoint or the presentation I have. Maybe I can, when I come to the regular class or theory class, I can show you once again. Okay, please remember this. Slightly a bit difficult, actually, slightly difficult this one. Okay, yes. Now coming to the next one, optical isomerism. Yes, a pair of optical isomers which are non-superimposable on their mirror images are called as enantiomers. as enantiomers. By the way, I don't know how much you are aware of something called as optical isomerism. I'll tell you briefly what is the meaning of optical isomerism. Let us say I have a test tube. I have some solution. Here. When I am passing a plane polarized light, what I am doing, I am passing a plane polarized light through the solution. Very often the light will be going straight for many compounds, but for some compounds the light will be bending towards right side or left side, only for some compounds. Such compounds which have the ability to rotate the plane polarized light to the right or left are called as optically active compounds. Optically active compounds. Once again, the compounds which have the ability to rotate the plane polarized light to the right or left are called as optically active compounds. So that is phenomena is called as optical isomerism. So we can find out optical isomerism in coordination compounds also. For example, you see two complexes here. I'll go for this. Yes, look at this. This is one complex. This complex has two isomers. One is this isomer, other one is this isomer. When I pass the light through this isomer, the light will be bending towards right side. When I pass the light towards this isomer, the light is bending towards left side, meaning they have same molecular formula, but the different what? Rotation of plane polarized light, one to the right, one to the left. Such compounds are called as optical isomers. Optical isomers. Okay, so those isomers, I mean this one and 2 together, call them as enantiomers. A pair of isomers which differ only in rotation. See, all the properties are same, but only light bending property is different for both. So therefore, compound 1, compound 2 are called as enantiomers. You will learn more about enantiomers, optical isomerism in the haloalkanes, halogen chapter. I'm not focusing more on those. So a pair of optical isomers which are non-superimposable on mirror images are called as enantiomers. When plane polarized light is passed through certain compounds, the plane polarized light is rotated to left or right. Just now I told you that. The isomer which can rotate the plane polarized light towards the right are called as dextroisomers. See here, I call this one as dextro. Why? Because light is bending towards right side. If the light is bending towards left side, we call as levo form. So we use short form D, we use short form L. So dextro means light is going towards right. Levo means light is going towards left. Next, optical isomerism is very common in octahedral complexes having bidentate ligands. So I'll show examples here. Right. So any complex having this formula will show optical isomerism in general. AA meaning what? Bidentate. AA is kept in the square bracket means bidentate ligand. So AA is bidentate ligand. So there are 3 bidentate ligands here. There are 2 bidentate ligands and B2 is monodentate ligand. We'll see examples here. So this one will show optical isomerism. Let's find out how to draw the structures. First one, what is geometry? I have 3 En. Each En will form how many bonds? 2 bonds, because bidentate ligand, total 6. So therefore octahedral. How to draw octahedral complex? I'll use like this. So I'll use cobalt. 1 up, 1 down, like this I have. So each En will satisfy 2 bonds because bidentate ligand. So this 2 will be satisfied by 1 En. This 2 will be satisfied by 1 En. This 2 will be satisfied by 1 En. So what we call this one? This is called as dextro form because light is bending towards right side. How to make lever form? It's very simple. You show a mirror, show the molecule in the mirror, show the mirror image. Meaning what? I have cobalt, one bond up to like this. When you show in the mirror image, left become right, right become left. Meaning this is left, right, it comes that side. So I get this will become En. Remaining, this top will not change. Kindly understand. So En will come here like this, and this En will turn this side. So En will come like this. So this is called as lever form. So this is D form, this is L form. So that's how you write dextro form and lever form, and both are the isomers, optical isomers of above complex. And for the last one, that is A15, if what I want to write, again what is the geometry? There are 2 chlorines and there are 2 En. Each En is bidentate, total 6 I have. So octahedral again. So platinum I have center, I have octahedral complex, so I'll make Cl here, so En will be coming here, one more En comes here. So this is your dextro form, this is your my D form. And if at all I want to make L form, what I should do? Show the mirror image, platinum comes here, so Cl top will not change, but this is right side will come to left. So Cl comes here, and this is left side comes right side. So En comes here, and this En comes here. This is your L form. So D form, L form. Be careful. By using this complex, we can also make geometrical isomers, which are cis form and trans form. I wrote optical isomers only for cis form. For trans form of A15 molecule, I cannot have optical isomers. Why? Because if you show the trans isomer in the mirror, both will be same. Meaning both are not different molecules, both will be same molecules. Therefore, only cis form of A15 example will show optical isomerism. Once again, only cis form of A15 example will show optical isomerism. Okay, you can see here this is cis form, while we have cis form and cis form. So dextro and levo form we have like this. Okay, so this is about optical isomerism. Kindly note the video is little lengthy. It will be very difficult to focus on a video for more than 10 minutes, 15 minutes. So I suggest you to take small breaks and use notes, write down the notes, practice the examples, try to practice the structures what I'm giving you, and get back to me with doubts. Thank you.